afternoon, day one of Devnexus. We sort of had a last minute request to pull together this thing, so it might be a little rougher than we hope, but the reality with working with tools is sometimes they work first time and sometimes you have to fiddle with them to get them to work, and so there will be a lot of live demos where hopefully everything cooperates. Let's just see where it goes. So that's a slide about me, and joining me will actually be Monica, and we're both Java champions, and we both work in the performance tuning realm, and so together we're just going to throw some demos together. We threw some demos together. We're going to show you, the hope is to focus on tooling. Our new reality is, we've known each other for I don't know how many years, and now we're actually working together on the same team, which is really kind of fun. I was really looking forward to that. I was excited when I heard that, oh, Monica's joining Microsoft, because at that time our company was being acquired by Microsoft, so it was, so it was all exciting when it all came together. And anyway, so I wanted to start, and basically, one of the things that that we've seen being pushed in the industry is just like this continuous profiling, always profiling, and the question is like, profiling for what? What exactly are we profiling for? Because the thing about profilers, it's a tool like any other. It's going to give us some measurements. It's going to tell us something, but the question is what it's telling us, is it actually relevant to what we're doing? Does it actually have any meaning? And I can look back at teams that I've worked with that have been execution profiling and getting performance gains with the execution profiling, but basically they're walking down some curve. It's like some sort of power curve, and where they were is on the flat part of the curve. So everything they were doing, they were just being guided by the profiler, but they're on this really flat part of the curve. And when we actually looked at the problem and did a higher level analysis and did a deep dive again and said, you're missing this thing over here because you're just execution profiling. And execution profiling is really good for telling you what your application is doing. Generally, and it has to be like some sort of frequency event or something like that for it to pick it up, but generally not very good at telling you what your application isn't doing or telling you other things about the performance characteristics of your application. So, before we just go blindly throwing tools at problems, what we'd like to do is just give us a little guide in actually how to select the tool that is going to be fit for purpose and give you the biggest chance of actually giving you information that's meaningful, information that's going to give you the likely the biggest performance wins. So our methodology is basically, we're going to look at this. We're going to start like with an SLA violation. I'm going to look at the CPU breakout and say, where's the pressure on the CPU? Is it actually in user space or is it in kernel space? And if we find that the pressure is in kernel space, then I'm just going to look at this and say, okay, I have an issue with the application interaction with the system. In that case, that's what I want to find out, is like, okay, what is that problematic interaction? What is it? And then, of course, I can use that information to figure out how to reduce the pressure on the kernel. Now, why are we interested in pressure on the kernel? Well, the kernel is really like some sort of provisioning system for hardware. And hardware is single-threaded. And single-threaded, you basically smack right into Amdahl's law, which basically predicts the scalability of your application. And so if you're hitting the kernel hard, you're hitting single-threadedness hard, which means there's very little room for scalability in your application. So we really want to fetter this out, figure out what's going on. And so there's a list of tools that we can actually use to figure out, okay, why is my application, what is my application doing that's basically putting all of this pressure onto the application? Now, if you're in a situation where it's just user space, so it's the application that's actually burning up CPU, well, in this case, what we're finding is that we're not meeting our SLAs, but we're not able to burn more CPU, then there's something else going on in the system. And what we want to do is try to figure out what that is. So we're going to say that this is like a non-dominant situation. And in this case, we just really want to ask the questions like, what is it that our threads are, well, more correctly, what is it that our threads are not doing? Or simply, do we have enough threads? Are we thread starved in some situation? So it might be, there might be a whole number of different ways that you thread starved yourself. It might be just that, it's single threaded and where it maybe should be parallelized. Maybe your thread pool is too small. Maybe all of your threads in your thread pool are off-hung on calls to downstream services, right? So there's all kinds of different situations. And one of the simplest things you can do in this particular situation is I can just look at what the threads are doing. Just do a thread dump. Very simple, all right? Now, if we're able to burn CPU, right, and our pressure on our kernel is fairly low, then I'm going to look at other questions. I'm going to ask, okay, are we memory efficient? Right? If the answer is yes, then I can get into CPU profiling, right? Because this is going to be an algorithmic strength issue. And of course, the CPU profilers are going to be very good at telling me where I have problems with algorithmic strength, right? But if it's memory strength, then we really want to do an analysis down here in the memory section. I think on the first demo, Monica's going to do a really nice analysis down in this area here. And this could involve actually, in terms of Java, tuning the Java virtual machine, or it could involve improving the memory efficiency of your application, or generally what it is a combination of both. We're going to improve the memory efficiency of the application, and we're also going to tune the garbage collector, right, so that the JVM is reacting to the memory pressure as effectively or efficiently as it possibly can. So, and I think that's pretty much everything here. So we'll cover some tools to try to cover some of these situations. We'll do as many as we possibly can in the time we have. So as you can see, how this is expressed is, we're going to say that things are passively dominant or aggressively dominant in the sense that if we look at the expression of pressure on the CPU, you're going to see that you have very low CPU or a cap, a max value CPU utilization that is far less than 100% when you're passively aggressive. So these are conditions in the machine where you cannot consume the CPU and nothing you can do at that point in time in terms of trying to utilize more CPU is going to help you. Generally what happens is that as you try to put more things on the machine to try to consume the unused CPU, your CPU utilization is going to drop, so you use even less. And that's actually predicted by Gunter's, the universal scalability law. Where aggressively dominant is just simply, we're just going to burn the CPU, so therefore you're just like maxed out. And when we're measuring this, we're going to tend to look at things in terms of kernel time and user time and idle time. So in this scheme of thing, all three measures are important. So idle time relative to kernel time and user time is just is always important. So we know. So most people are just looking at, I don't know, if you look at your charts you have on your screens in the office, right? They're going to say total CPU utilization. Yeah. So to me, that's kind of like a meaningless measure because without actually understanding these breakouts, it's hard to tell if that total CPU utilization is actually your max CPU utilization, or if you actually have more CPU headroom, and that there's other issues that are causing you to miss your SLAs. So a common tool that we'd actually use, just a very simple command line tool called vmstat is one you can use. And as you can see, what I can do is I can look at the breakdown here. So I have a user time breakout and a system time breakout and an idle time. In this case, I have wait time. And if I do the analysis on this, you can see that there's very little user activity that's creating a huge amount of pressure on the kernel. Okay? So right then and there, I know, that something is causing my application to put pressure on the kernel, and that's going to limit not only my performance, in this case, it's going to limit my ability to scale. So effectively what I want to do is I want to go through the rest of the counters and try to see if I can get a hint as to what's going on. The wait time column is going off the charts here. that's an indication that there's block I/O happening. So this is like something backed up on disk activity. And also we have a significant level of context switching. So that's the CS column beside the user column. I don't want to go in too much depth so we can see some of this live. But in this particular case, you can see that there's possibly what we're doing is like a lot of very short writes. They're going very quickly. And what that's doing is aggravating the thread schedulers, and that the thread scheduler is once you hyperactivate the thread scheduler, then of course the system time is the kernel time is going to go up. Of course that's also going to affect your ability to saturate CPUs, right? Because if you're always waiting on the thread scheduler to try to figure out who should be running where, then nothing is running. Okay. Another important aspect of this whole thing is what I call like time budgeting. And this is just a very simple thing. So this is an actual time budget we did. It was a pre-Black Friday, oh my God, our system doesn't perform type thing. And in this case, I actually had to do the whole engagement without any access to anything. So I got some friendlies inside to actually say, can you get me some measurements and stuff like that? So it was just a simple 3-tier application, but it was clustered out. It was not that large. It's like 300, 400 VMs, something like that. So, fair size, but not overly big. And so we just like got some timing information from different sources and stuff like that. And we actually built out this time budget. And we actually look at the time budget, something always is going to stand out. It's going to be something there that basically says, hey, what's happened there? Can anybody point it out? It should just jump off the page at you. Does anyone see? Just shout it out. Well, if you look at it, like the calculation between 0.5 and 6 says 200 milliseconds of a 300 millisecond time budget. So 2/3 of our time is spent right there, right? So this is like database, Oracle, doesn't really matter, but the transaction is cleared because the database guys are coming back and saying, hey, it's like we're clearing in less than a millisecond, so like that's awesome, right? But where's the other 199 milliseconds to get this packet of information back into the application server? So the clear problem is like, what is happening there? And so you can see just having that view on the system meant that we were able to very quickly go in and figure out what's happening right there. So we take a combination of these two techniques and put them together. It's a very powerful way of focusing, where the problem is and what the nature of the problem is, and then what tools should I use to further characterize that problem so that I can understand what it is that I'm facing. Okay, so that's just a very, very quick introduction to our demo. Into our things. So as we said, this is like live performance tuning. So minimal slides. We're going to have just some tuning here. So I think before we do the tuning, what I wanted to do was, I forgot to start up that part of the demo, but it's okay. We'll get it right here. And here, okay, it's starting up. So one of the things that is anyone anyone here involved in manufacturing microservice architectures and things like that? 1, 2. I guess it's after lunch coma. Nobody's got their arms working. All right, so you can do a stretch here. Just say, it's cool. Okay. So I'll ask the question: who here is not involved in constructing microservice architectures? Okay. So that's even more than we're actually involved in. Yeah, okay. So I'm going to assume everybody else is sort of, I don't know what a microservice is, or two is like, I'm just too lazy to put my hand up, but it's okay. But one of the things that we found is that we're observing some really interesting latency issues with microservices having to do with pauses. So I just decided to build a couple of just quick demonstration flags. Okay, I notice you can't actually see that, so let me fix that. Mirror, awesome. Okay. Yes, here we are, scary code. Let's get rid of the scary code. More scary code. Okay, so what I want to do, so basically, you know, the microservices idea is like I got all these services and all these different nodes and everything, and then if I'm going to execute some query, I'm going to go off and collect data from all these nodes, gather it up, send it back to the user somehow. And what we're noticing is that you can get some pretty long call chains in terms of the number of nodes that are involved in collecting the data and getting the services. So what I do is I said, okay, let's consider a call chain of like 100 nodes. Here, let me, for those of you who didn't make it to the closer to the front, how's that? Okay. And I said, okay, let's, in this case I call it GC overhead, but let's just say there's a pause events in the system. And there's all kinds of sources of pauses. Garbage collection is one, so this is just sort of a feed into what Monica's going to talk about here. But you can see what we have to the left of the, you know, and down from the line is basically probability that your request is going to go through this whole architecture and not accumulate any latency due to some pause event in the system, assuming like there's a 5% probability well, there's an overhead of 5% in pause, right? So that's kind of interesting. So, you know, we can do, I think we were using 20 before or something, so you can take a look at this and see that, you know, there's, so you can play with the numbers sort of to get an idea, like, okay, this is how many microservices I have in my chain. You know, what is my latency picture going to look like just because of how I constructed things and nothing else, right? There's nothing to do with how long it actually takes to service the call itself. Okay, so that's kind of fun. If we come back to, whoops, here, whoops, that's a different application, which I'll just close down here. Too much coding going on here.
So what is the y-axis? That's the number of
yeah, it's the number of pauses in this case here. So it's like we're looking at it's probability of no pause. Sorry. Right. So you can see that by the time we get down to a call chain of like 20, there's something like a, what is that? About a 15% probability that your request is going to go through this system and not see some sort of stall, just because of how the system is constructed. Okay, so let me see if I can actually get this to cooperate. And we'll just take a look at one of them. So we have like a pause distribution chart here and stuff like that. Where did it go? Running? Okay. And in this one here, whoops, that's the wrong one. Where did it go? I've lost my window. Keeps seeming to wanting to run the same one for some reason. That's what I said, you know, that's when tools start. Call chain chart. Okay. This is silly. Sorry. Let's try that one. Okay. So in this one here, if we take a look at this, so say we have 20 nodes again, and we have our same GC overhead and everything like that, and I'm actually putting an average pause time out here of like 100 milliseconds. This is actually the number of pause events the probability that, you know, any request going to the system is actually going to see either 0, 1, 2, 3, 4, 5, 6, 7. So you can see with a number of nodes of 20, you know, there's the probability of pauses in this case here. It looks something is wrong, funky with the number here, but you can see that by the time we get to, very likely to see 2 or 3 or 4 pauses, like in this range here. By the time you get down into this part of the curve, you can start seeing, like, you know, it's very unlikely you're going to see 5, 6, or 7, or 8, or even like 20 pauses in this case, or 30 pause events in this call chain. But anyways, you get the point that all of a sudden, when you start looking at the latency picture from your microservices architecture, pauses really start to matter because this is just additional latency that's just there because of how you've constructed things. So that's something interesting. So I think Monica is going to come in and talk about garbage collection, which is a known source of tail latency. And so with that in mind, I'll just flip over to her and she can talk about, whoops, don't worry about that. So during some of the demonstrations where things will be running for a period of time, so feel free to put your hand up and ask questions, and during the demonstration we will happily start answering questions if you have any.
So the reason I wanted to show this benchmark, or micro benchmark, is because during my last presentation at QCon San Francisco, I was co-presenting with my peer at Intel, and he brought this up that he ran DeCapo. So if people are familiar with Java benchmarking, DeCapo has been around since 2004 or 5, and they have gone through various iterations of improvements and additions to the benchmark. So this is the charts. These are the charts he presented to me. I'm sorry. He presented to me, and one of the things he told me is that JDK 11 shows a decrease in performance for DeCapo. And I was thinking, based on what the benchmarks do, or what I thought they do, why would the JVM matter? Why would the JDK matter? And then I asked for, we went through the methodology that Kirk mentioned earlier, and we did find out that it was in fact memory. And I'm going to show you how we did it. Okay? So just to make sure that everybody understands what benchmark suite I'm talking about, it's DeCapo right here. And I went through like these things, and I found that Eclipse right here is showing the most variance, right? Difference in performance. And according to the benchmark website, it says Eclipse apparently executes some of the non-GUI JDT performance tests for Eclipse. So for those that don't know what JDT means, it's basically the dev tools. So which means your the Java C, the source code formatter, or even the file indexer and search. So apparently Eclipse benchmark does all these things, okay? And again, I did not understand why JDK 11 would show difference in performance, so I decided to run it myself. So in its simplest, and I got the latest version, which is an evaluation right now, and it was released last year, still in evaluation phase because they're looking for feedback. So I do a basic run. And I should have shown that I'm running with Java 11. And one of the things that you get with Java 11 is the G1 GC garbage collector. What I'm trying to build up a story here is that the reason we moved from parallel garbage collector in JDK 8 to G1 GC in JDK 11 is why we see the difference in performance. But we'll go step by step, trying to observe that first and then correct the problem. Okay, so it shows here the DeCapo took 32.3 seconds, and now I want to go and look at a log. The reason I look at a log is easier for me to understand and grab from the log, and I know what I'm looking for. But for people that need tools, we all have Sensum, and I have it running right here, and I'll open the log with Sensum as well. So, and this is the default log here. So this is just out of box. I'm running that. And Sensum provides you a pretty good information right here. So if you noticed what Kirk showed earlier, he showed some JavaFX charts, right? And then I have my own. So one of the things about performance analysis is that we write our own tools. And this tool was written by Kirk's company, which got acquired by Microsoft. And prior to using this tool, I used to have my own scripts in jFreeChart. So basically, I take the log, parse it, and then have jFreeCharts show you the information. But with this Sensum tool, what you can see is all the information in one place. So I'm gonna, because I know what the problem is, I'm gonna skip to the problem, and I'm gonna show you the chart here. So what you see here, humongous reclaim. It's showing about the face time percentage is about 45% right here. And it takes about 30 to 31 seconds. And what I'm gonna do also is gonna match it with the log, okay? So because, again, I knew what I was looking for, so I got to put the right information. But what you see is humongous allocations are triggering this young collection, basically initial mark phase. And before I go and dig deeper into this, I want to give you a background on what all these things mean, okay? So I'm going to go back to the presentation very quickly, and I'm going to talk about, okay, right here. So let me go into play. There you go. Oh, right. Oh, you guys can see it correctly. Okay, so, sorry. So I'm just going to stay here. So people probably know already about the heap, right? We know about this contiguous space, the Java heap, right? And with the introduction of these newer collectors like G1 and ZGC and Shenandoah, what you see in OpenJDK is that we're moving towards regionalized heap. So what does that mean? It means that the same contiguous heap is now a bunch of heap regions, okay? So with G1GC, you also have the generational concept, which is similar to what you're used to with respect to parallel GC as well. So you have the young generation, and then you have the old generation, okay? And of course, with G1, we have the regions. So at any given time, you have a bunch of young regions or a bunch of old regions, okay? So currently, ZGC and Shenandoah are not generational, but they are regionalized. And G1GC is the only one right now that's regionalized and generational, okay? With G1GC and with any kind of regionalized heap, you have the sense of occupied and free regions, okay? So at any given time, what you could have, because of if it's a generational GC, at any given time, you can have a bunch of regions that would be occupied, right? To a heap, doesn't have to be contiguous unless it's a humongous object, okay? And I will explain that in details. So we have a list of free regions at any given time, and then we have a bunch of occupied regions. These regions, because of the generational nature, could be young or old, or like I mentioned, could be humongous as well, okay? And a G1 heap simplified could look something like this. So you have a bunch of Eden and survivor regions, and then you have a bunch of old regions, and then humongous, since it's contiguous, they have to be next to each other, okay? So let's go back to the demo. As I showed earlier, we saw that we had an issue with humongous, okay? So the easiest way is to figure out your heap region size, right? Because I was talking about regionalized heap, right? All right, so right here at the top of the log file, you see the heap region was 1 meg. So I will talk about why that is a problem, but I will show you the solution while it runs. We'll come back and I'll talk about the problem, okay? Okay, let's go back and look at why humongous regions were a problem. So, with UNGC, there are different. The concept of humongous is when the object is 50%. The object size is equal to 50% or more of your region size. Okay. So, given the three conditions that I showed, right? Objects less than 50%, object is greater than or equal to, and then object far greater than the region size itself. Okay. So the first object that was less than 50% is considered a normal object, normal sized object, and will be allocated allocated into the young generation, because that's where most allocations happen, in the young generation, in the Eden region. Okay. But the second one, which was greater than or equal to 50%, will actually reside in the old generation. So because we think of humongous objects as a place that we kind of long-lived, so we don't want to keep on moving it, because remember, the copying collector moves live objects around and kind of ages them. So we don't want to do that with such big objects, because copying time is the major stop the world time, actually, of your pause. So we want to make sure we allocate it directly in the old region. So it's in the tenured space, right? And for the one that's greater than the region size itself, it will need more than the region size itself, okay? So what we have is that anything that's not humongous is allocated, it follows the same fast path allocation out of Eden in the young generation. And anything that's humongous or even greater than the region size itself, it'll be out of the old generation and may need contiguous regions, okay? So let's go back to the demo. So right now, remember I grepped for humongous, and we can look at the log as well. So we can grep for humongous here too. And we don't see any humongous allocation. So what did I do, basically? What I did is I told G1 to increase its region size, because I knew that humongous allocations were the problem. And because we were doing humongous allocations, it was actually starting the marking cycle earlier, and that was affecting the thresholds, and we were unnecessarily doing mixed collections, or we were trying to clean up for mixed collections. So basically, we're starting a concurrent mark, which may or may not lead to mixed collections, but that's waste, because marking means you're tracing from the roots, the GC roots, and then you go down and mark all the live objects. So that is wasting time if you don't need it. So I told G1 that, hey, I know that these objects are not going to live that long because my benchmark is only 33 seconds or whatever. So I want to make sure that you can allocate it as a regular object. And in order to do that, I changed the region size so that the object is considered normal and allocated out of the Eden space. And that's why I got rid of my humongous allocations. So that was one of the things. And what was funny is that if you see and I was going to show visual VM and stuff like that too, but that's okay. I think I'm going to give it back to Kirk here. But the point is that when let me just start a run here anyway. Let's go to Visual VM. One of the fun things about Visual VM and tools like Visual VM is that you can literally see you can monitor the application that you're running, right? So for now, I'm just running the same thing with 4 megs or whatever of region size, and you can see your class loading activities, the threads, heap, how the heap is going, and then if you have installed these plugins like Visual GC. And you can actually see a histogram of all the activity from the beginning of the application. Okay, so there's going to be a talk later today where Ludovic and I will talk more about startup time and everything. So that's at 3:30. So please do come to that if you want to see more of get more information on the class loading stuff. The other thing that's important about Visual VM is you can do profiles, and memory profile will help you. But going back to what this benchmark was supposed to do and what we are actually chasing is the object size. So one of the things that we advocate is about characterizing your benchmarks. So if you think your benchmark is doing A, but it ends up doing something else altogether, then you haven't characterized your benchmark correctly. And then the way you would know if characterization is correct is by validation. So with that, I'm going to give the stage back to Kirk. Thank you.
Okay. So this is a way of reducing GC if you're escalating on the pause time. I think this is something that's fairly important for dealing especially in microservice world, where we've seen that pause times are very the architectures are very sensitive to pause times. I don't know if you can see things yet. We're there. Here. No, I can see. Oh, you can see. Because even if you can if you look at this particular chart here, if we just knock this down to 3%, and I'm going to redo the same calculation and stuff like that, you can see that all of a sudden, the dynamics of the situation really change considerably in terms of where the contributions are coming from. If we take this up to even 10% or worse, you can see all of a sudden we're just getting our latency due to pause times is just going to just get worse, because we're just going to encounter more of these 100 millisecond pauses. So cool. What I want to do next is just run a web app to throw some other some other tools at you, like Visual VM. Has anyone been using Flight Recorder and stuff like that? Yeah, so we have a few people using Flight Recorder also. Let's just get rid of some of this stuff here so we can actually take a look at it. So what I have is a web app that's running. Well, I don't know why I have mail open, so let's get rid of some of these silly things that are running. So I have this application server that's running, and it went really bad, so I had to kill it and everything. And so what I'm going to do is I'm going to load it. And what you're going to see is that if I put load on this particular application server, it's going to run out of memory. Rather than go through the exercise of saying hey, it's run out of memory and stuff like that, we're just going to say it's run out of memory. And now we got to figure out, what's going on here? Why is it running out of memory? This podium is funky. Okay. What I'm going to do is I'm just going to say, okay, well, let's put some load on this thing, and let's just try exposing, why this thing is running out of memory. In this case, I'll assume a memory leak. Of course, there's a whole protocol we want to go through, but I just want to focus on the tools. So the first tool I want to focus on is trying to see, okay, what does this thing look like with Java Mission Control, right? So I'm going to take Java Mission Control, which is basically the visualizer for what's happening in Flight Recorder. And so I'm going to go look at my JVM browser over here. And so it's saying, oh my, I got all these wonderful things running. Actually, I can get rid of some of them to clean up the picture. So let's just shut down IntelliJ. I don't need that anymore. So exit. Okay, fantastic. So that should get rid of a lot of this stuff. Right. Okay, so here's my web app. And so what I'm going to do with my web app is I'm going to say, okay, let's get a flight recording of what's going on. So Flight Recorder is going to eat off of probes that have been injected inside the JVM. So it's going to activate these probes and going to start collecting data. Now, it does this based on a template, and I'm not going to go into too much detail here because we don't have time, and there's good blog entries about how to do this, but you can create your own events, and you can customize the templates and stuff like that. The only thing that we're actually interested in here is making sure that we get enough information to get information about what's going on with the garbage collector. So in this particular case here, you can see I'm going to make sure that I get the object types, the allocation stack trace, and a path to a GC route. Of course, the garbage collector can only collect things that are not attached to a GC route. So we want to find everything that's attached to a GC route to try to figure out what's going on. And then after that, it's just an inventory problem, which is count things. So it's not that difficult. So we'll take that. We'll finish, which means I am now in the process of collecting data. So now I'm going to fire the recording, and the recording is going to go for another 50 seconds. So this is a good time for questions. Anybody have questions they want to fire at us while we're waiting for the profile to end? Come on in. Don't be shy.
Those earlier graphs that you had with probabilities, that was just simply a mathematical analysis of the topology which you had, right?
That's exactly right. It's just a simple mathematical topology. It was actually took, since we're not really mathematicians, we're just pretend mathematicians. It took us a little while to build that, so we're like really kind of proud of myself for being able to do this, but but it is a mathematical model. It's really just an application of binomial theorems. So it's nothing overly fancy, but I'm still proud I was able to do it. So, okay. Anyways, so we're down to it's done. Okay, so that one question was just timely. Thank you. And so if we look at what's out here, it's basically saying, so we have this little bit of analysis going on up front, and there's an indication here there's a problem with heap lie set trend, which is like not really a surprise because we've already run out of memory. And so if I just open up and take a look at it, saying like lie set seems to increase from 36.1 speed. Oh, it's increasing 36.1 megabytes per second during the recording. This hash map, session, link list node, I don't know what that is. But effectively, you can see that there's something going on in some sort of linked list node inside of our application. So it's sort of giving us a hint as to what may be going on. It's kind of, it's still kind of sketchy in my mind as to what's happening. I can look at this view over here, which is actually giving me a histogram of live objects. And you can see I like object arrays, int arrays, hash session manager. Seems rather interesting with hash session. Okay, it's a web app, so that there's sessions involved here may not be all that surprising. Hash nodes, and we can open it up. And you can see it basically we can walk down and we can finally, hopefully, figure out that we have a crumb trail. Crumb trail doesn't sound. Has anyone seen the JDK class called crumb trail? No one's got their hands up, so I'm going to take that as a no. Okay. And hash map in here, hash map node. So all of a sudden you can see that instead of having like really here's a closing price list. So I forgot to tell you, this is like a stock history application. So it's getting me stock prices. But you can see all of a sudden I got it. Okay. Closing price list. So now I have some structure, right? So if I go into the application, I probably should see a crumb trail. And with the crumb trail, I'm going to see that probably what I'm doing is I'm attaching things to the crumb trail in these hash maps and array lists and things like that. So I have closing prices actually in a closing price list. Not really a surprise, but anyway, so now I have really good information. And the one thing you can notice about Flight Recorder is that the impact on the runtime to collect this information is incredibly low. There's not really a heavy overhead for doing this. Now, the way we would do it in the past is I will go and just hopefully restart this thing. Okay. Don't try this at home. Okay, there. Don't do that at home. Do that often enough and you will definitely have some fun. So I'm just going to restart this again. Instead of using the flight recorder mission control, what I'm going to do is I'm going to use Visual VM. So Monica started playing with Visual VM there. And the funny thing is with Visual VM, it's really the only profiler. With the JFluid profiler, which is included here, is the only profiler that gives me what's known as a generational count. And what a generational count is actually it's telling me how many different generations of a particular class of objects do I have, right? And the fun characteristic of a memory leak is that they're going to have high generational counts. Most in normal application, your generational count is going to be like 0, 1, 2, 3 or something like that. When you have a memory leak, what's going to happen is that your generational count is going to approximately equal the number of garbage collections that have run. So that's a really good metric for finding memory leaks. So if we can go out to collecting, I'm going to go to the profiler. I'm going to look at the filters. Whenever you use a profiler, make sure you understand what you're filtering. Do not filter the bottleneck out of your profile. As a little piece of advice. Let's see what's going on here. Whoops. I'm just going to take, okay, good enough. Oh, right, that's CPU. So let's try this. And make sure you know what you're working with. Okay, so I'm going to track all live objects and arrays. Because I'm at the position here where I don't know what's leaking, right? Because we haven't seen the last profile yet, have we? No, don't think so. Looking at time. Okay, so let's go and attach the profiler. And see, there's my generation right over there. So what I'm going to do is I'm going to, right, I'm going to sort on generations. And the thing is, when I'm actually looking for something with a high generational count, what I actually want to look for is a domain object. I don't really want to find strings and cars and things like that. The domain object is going to be a much stronger entry point into the investigation. So what I'm going to come back over here and do is wipe this out, look at our aggregate report, and fire off our test harness, and let's be leaking. And then I'm just going to watch what's going on here. So let me make it big so you can actually maybe get an idea what's going on. So you can see the generational count climbing here. So it's not just, as you can imagine, it's not just the closing price that's going to leak. It's going to carry a lot of things with it. It's going to carry like the structures in the hash map. It's going to carry the structures of the array list, and all of these other things are going to travel along with it. And as I said before, really what I'm looking for here is, there's my high generational count. We should get a cliff event here someplace where you can see the generational counts are going to drop fairly dramatically. But if we come back over here, there's my closing price list. You know, strings and bytes that come along for the ride, not really that big a thrill or whatever like that. So, okay, so now what can I do? I can basically get a snapshot. That's my allocation stack traces. So I can look at closing price, and I can now, with this, get a view of my causal execution path to the allocation site. So I know where in the code this is happening. I can come back and I can get a heap dump. And with the heap dump, once we get that loaded, what I can do is I can start looking at the relationships between the objects, so I can understand, what these things are pinned to, and what it looks like in memory. So I know it's leaking, I know its relationships, I know its causal execution path. I can use all of this information now to start debugging the problem. And you can see we can go through this exercise very, very quickly. Generally, time to resolution, depending upon how the tools cooperate, is between 15 minutes and 30 minutes. I know at least one of my colleagues in the room is laughing at me right now because I said yesterday, I'll build this plugin in 20 minutes, and actually 2 hours later, I'm still going like, there's still something wrong here. But anyways, yeah. So yeah, it's 15 minutes plus or minus 2 hours. How's that? That's a good random estimate, right? I mean, can you give a better estimate to your manager? Ever? I'll tell you. Okay. And we're still loading the heap dump, and it's going to take a while. So in the interest of time, because we are now at, okay, we can start taking time for questions. Yes?
So when you talked about the flight recorder, you mentioned that it has no impact on the performance.
That's correct. Very low impact on performance in most cases.
Use that one, but on Visual VM, whenever I use the profiler instead of the sampler,
yeah,
the JVM's free.
Yeah, it has a very, very high impact on the JVM, and it has a lot of other impacts on the runtime also that you may not notice. Like for instance, what I'm going to do is I'm going to inject code into the runtime, and as I inject code into the runtime, I'm going to wrap data that's being created, and all of this extra code there is going to start disturbing the optimizers, which means that all of a sudden my runtime is going to look different, and my profilers are going to start lying to me. They're going to tell me things that are actually not true in my runtime. So I have another demo that I usually do for that, where you can see that I have this really hot allocating object. It's like, like it's super hot, and I find it and I fix it and I run it again, and the performance of the application is the same as it was before I went through all of that work. And the question is why? Is because the optimizations were disturbed to the point where it wasn't able to basically remove that allocation from the code, right? So one of the things to do is like an allocation site elimination or reduction. And the profilers prevented that from happening. With JFR, the way that they've actually instrumented, it's not going to cause the same type of disturbances. It will still disturb, but not in the same way. Okay?
So my question was like, for that slide recorder, isn't that one of the commercial features of the...
Yes. So JDK8 is commercial unless you get a backported version of the open source tooling. So the one that I'm actually using here in JDK11 is open source, and you can use it in all of the environments you want to run it in. The commercial version with JDK8 is for test environments only, not for production environments. Okay?
So the flight recorder you were using is open source?
In JDK11, absolutely. Fully open source, and there's some versions of the JVM that you can download where they backported the open source version to JDK8. So as long as you're using their JDK8, I think Zulu is that way as one. I know there's a couple of others that have backported also. Okay. Any other questions? Are we stuck? Oh. For some reason, I don't think this. I think the heap got bigger than digital VM Lite. So this is the other problem with doing heap analysis, that it takes a lot of memory. So I think I allowed the heap to grow too big. So it's 81% done. Are there other questions? I guess there's other tools that I do use, and so what I'll do is I'll just quickly. So if we look at some other tools that you can use for diagnostics, there is, let me just make this bigger, since we have like a minute or two left. So if I do a J command -L, I'm going to see all of the JVMs that I can actually attach to. So in this case here, that's my application server. So if I do a J command with the PID and I type in help, it's going to give me a list of all of the commands I can actually send to the JVM to actually get information out of it. It might be useful information. So one of the things that we commonly do, which I mentioned, is actually do a thread dump. So in this case, what I can do is I can say, let's thread dump that, and let's put in that like a thread.tdump, like this. Okay, so that's going to basically create this thread dump. Now, one of the other tools that I find very interesting for actually analyzing the thread dumps is this thing called TDA. And so what TDA is actually going to allow me to do is open, let's see, where is that thread dump at? Oh, right, okay, it's right on the desktop. So we can just go back to TDA. I can go into desktop. Oh, right, this one. And stock. And I can hit my thread tdump, open it, and it nicely categorizes all of the threads for me into different little categories. And you can build your own categories also. So you build up filters and filter sets, and so you can find out all kinds of different things. So in this case, you can get an idea. There's 53 threads, so we can look at the thread counts, and we can, basically it's going to partition the information for it. But it's really nice. To be able to find out different views of things. So this is a view from a lock point of view. So if you have a hot lock and you do a thread dump, and you have a lot of threads that are blocked or waiting for the same lock, then this will just show up red. And so you can very quickly find different things. So, and if you can build your own filter sets, you can look for your own conditions or your own specific things that you might find within your runtime. Oh, here we are. So I can look at objects here. I can find my closing price. When I open up, You can see this is what the closing price looks like. And I'll just make that bigger so you can read it in the back. And we can start looking at the references. So what I can do is I can trace all the way from this object all the way back to a GC root to figure out what's going on. And I think when we finally do that trace, we're going to see that we're going to get pretty much the same result as what we saw with JFR. Awesome. So now we can just go in the code and debug, fix the problem, and life goes on. Okay. Any questions with that? Anything from you, Monica, to finish? That's good. Okay. I think that's about all the useful time we have for showing things. So thank you for attending.